In the first video, we saw some introduction to real numbers and why every number is not a real rational number. To actually do anything meaningful in math, you need to have some proper definitions set up. Okay, so let us start with definitions. Definitions. Okay, so what is the first important definition we are going to need? It is a set. Okay, a set is a collection of objects with a very specific criteria that we should be able to distinguish whether an element is in the set or not. A collection of objects with a precise rule, precise criteria to tell whether elements are in a whether an element belongs to a set or not. To tell whether an element belongs to the set or not. We are not going to deal with set theory, so everything we deal with will be sets. We will not be dealing with things which are not sets. Okay. We will say write x in A. Okay. Reads x element of A if x is an element of the set A. If x is an element of set A. The short way of saying it is x is in A. Okay. If x is not in A, write x not in A. Okay, so that's the way we are going to write x is in A, x is not in A. Okay, for A and B, two different sets. Let me first write A is called empty set denoted phi if A has no elements. Okay, if A has elements, so otherwise A is non-empty. Okay, so this is how we distinguish an empty set and a non-empty set. If A has elements, it is not empty. If A does not have elements, it is empty. If A and B are sets, if A and B are sets, and every element of A is an element of B, and if every element of A is an element of B, which i.e. x in A implies, let me write down, i.e. if x in A implies x in B, then we say A is a subset of B. Read A subset of B. Okay. In addition, so generally it is written this way. Okay, I'll write it this way. In addition, if there exists x in B such that x is not in A, then A is a proper subset of B. Read a proper subset of B. Okay. Note, A is always a subset of A. Okay. And if A is a subset of B and B is a subset of A, then we call the sets A and B to be equal. Okay, that means the two sets are equal. Okay, oftentimes people don't write the proper notation. Okay, sorry, they don't write the lower equal of some people write. So let me do it this way. Note, some books use A, B as subset and A not equal, subset not equal as proper subset. Okay, so most of the times we'll be using subset. They'll generally be proper subsets. Okay, so this is our standard notation definitions. Now some other definition, a definition of order. Definition: let S be a set. Let S be a set. An order relation on S and an order relation on S is a relation generally denoted smaller than with the following properties. With the properties first, if x and y are in S, if x comma y belong to S, then at least one of the following should hold true, and exactly one of the following should hold true. Then one and only one of the statements holds true. Either x is smaller than y, or x is equal to y, or x is greater than y. Exactly one of these three things should be true. And the second, it should be transitive. If x comma y comma z in S and x smaller than y comma y smaller than z, then x has to be smaller than z. Okay, the order should be properly preserved. Okay, we generally say read x smaller than y as x less than y, or x smaller than y. Okay, great. Sometimes you use y greater than x. Sometimes y greater than x is the same as x smaller than y. Okay, you might want to use one in terms of one or the other. X smaller than or equal to y is x smaller than y, or x equal to y. Okay, this is the negation x smaller than or equal to y is the negation of x greater than y. Okay, so now that I have the definition of an order, I will define an ordered set. Well, what is an ordered set? It's what you would expect. Definition. An ordered set S is an ordered set is a set S with an order defined. Okay, so a set which has a very particular order defined on it means that it is an ordered set. Note on Q R greater than S if and only if R minus S is a positive rational, positive non-zero rational, because 0 is not positive. Okay, definition. I am going to start writing definition in this shorthand notation because the word is pretty long. Okay. Last time I talked about the least upper bound property. What is the least upper bound property? Here's what the least upper bound and in fact even an upper bound means. Suppose S is an ordered set. Suppose S is an ordered set with and E is contained in S. It would be equal if there exists beta in S such that beta greater than or equal to x for every x in E. So this is for every slash for all. Okay, so I'm going to introduce this shorthand notation pretty early so that because I'll be using it throughout the entire course. If you have taken 421 or any of the other classes, you might be familiar with it, but in case you're not, please pay attention. This is standard notation. This is there exists, and this is for every. This is very standard notation. It'll pop up constantly. Okay. If there's such a beta, it need not be in E. It only has to be in S. If there's a beta in S such that beta is greater than or equal to x for every x in A, we say E is bounded above. E is bounded above and call beta an upper bound of E. Call beta an upper bound of E. Okay, once again, beta need not be in X. Okay, lower bound defined similarly with beta smaller than or equal to X. Okay, so now I have an upper bound. What is the least upper bound? Definition. Suppose S ordered set with E subset of S and E bounded above. And E bounded above. Okay. Suppose there exists an alpha in S such that with the following properties. With following properties. What are the properties? Well, first, alpha is an upper bound of S. Alpha is an upper bound of S. And second, if there is another upper bound, if beta, which is, let's say, strictly smaller than alpha, is if beta is strictly smaller than alpha, then beta is not an upper bound. Then beta is not an upper bound of E. Okay, this should have been an E, not an S. Then we call that, then alpha is called the least upper bound. Least upper bound of E. Okay, I'm not going to prove that there is a unique such bound. Well, take any two alpha and beta, one of them has to be lower because S is an ordered set. Well, that contradicts that if alpha is smaller than beta, then it contradicts that beta is also a least upper bound. So there has to be a unique least upper bound. Okay, least upper bound of E and denoted alpha is equal to sup E. Read supremum of E. Supremum of E. Okay, the greatest lower bound, similarly, the greatest lower bound, greatest lower bound, or infimum bound, or infimum, or infimum of a set E of E is of E which is bounded below, which is bounded below. Okay. Actually, let me write this properly. The greatest lower bound, or the infimum of E which is bounded below, is defined similarly. And we will denote it by alpha is equal to infimum of E. Denoted alpha is equal to infimum of E. Okay. Examples. Consider the sets A and B defined in the previous lecture. Consider A and B defined in part 1. A is bounded above. A is bounded above. B is bounded below. Okay. And why? Well, anything in A is a lower bound for B. Anything in B is a upper bound for A. However, A has no least upper bound in Q. A has no least upper bound in Q, and B has no greatest lower bound. B has no greatest lower bound in Q, right? If we extend it to R, then that would, but as of now, I have no idea what R is. I have not defined what R is. So, such a thing is there. Okay. Note, more than one set can have the same supremum and infimum, obviously, but it does depend on the set whether the supremum or infimum is in the set or not. If, for example, E1 is equal to E1 is the set of R in Q such that R greater than 0, and E2 is equal to set of R in Q such that R greater than or equal to 0, okay, then infimum I and F infimum of E1 is equal to infimum of E2 is equal to 0, but 0 belongs to E2 and 0 does not belong to E1. Okay? You can also have that the supremum is in the set and the infimum is not. Let E is equal to 1 over n such that n belongs to the naturals. Okay? So it's going to be 1 half, 1/3, 1/4, 1/5, so on. Then infimum of E is equal to 0, and supremum of E is going to be 1. Okay? You should check this. If you're not super familiar with infimum and supremum, this might be slightly non-trivial for you. You might need to think about it. Supremum is 1 because, well, that is the largest number in the set, right? But but infimum is 0 might need some convincing for yourself. Think about what is the smallest number that is larger, what is the largest number that is smaller than everything in E, and try to prove that it's 0. Okay? Okay? Then I get, therefore, infimum of E does not belong to E, but supremum of E does in fact belong to E. Okay, so it could happen that the supremum is in the set and the infimum is not, or vice versa. Okay, this is my upper bound, lower bound, least upper bound, least lower bound, greatest lower bound definition. An ordered set S, an ordered set S is said to have the least upper bound property, the least upper bound property if the following is true. If the following is true. If E is in S and E is not empty, E non-empty, and E is bounded above, and E bounded above, then supremum exists. Then supremum E exists in, well, we can't say it should exist in E, but it should exist in at least in S. Okay, this is the property we would like to have, and this is what is called the least upper bound property. We have shown before that Q does not have this. Okay, now we will show that there is a very important thing, that the least upper bound property also implies that the greatest lower bound exists, because otherwise we'll need to define two things: the least upper bound property and the greatest lower bound property, right? But no. So theorem. Suppose S is an ordered set. Suppose S ordered set with least upper bound property. Okay, and let B belonging to S be such that, and B belongs to S be non-empty, and B is bounded below, not above, and B bounded below. Okay, well, I want to show that the infimum then exists in S, right? So let L be the set, let L be the set of all lower bounds of B, of all lower bounds of B. Okay, then alpha is equal to supremum of L exists in S, and in alpha is equal to infimum of B. Okay, in particular, infimum B exists in S. Okay, which is to say that S has the greatest lower bound also for every set B. So it has the greatest lower bound property. Okay, proof. Well, since B is bounded below, L is not empty. Right? Because B is bounded below, there is at least one lower bound. Well, that lower bound is in L. Therefore, L is not empty. Also note that since L consists of L consists of y such that y in S satisfying y smaller than or equal to x for every x in B, it is automatically true that every x in B, since this is true, therefore every x in B is an upper bound. It is an upper bound of L. Okay, so therefore L is bounded above, and as we assumed that B is non-empty and is non-empty, and well, we don't need that actually. L is bounded above because there is at least one element in B, because B is non-empty, that is an upper bound of L. Okay, therefore, sorry about that. Therefore, there is a supremum of L. Therefore, there exists supremum of L. Let me just. Therefore, L has a supremum. Therefore, L has a supremum. Call it alpha. Okay. Now, well, let us see. Since it is the supremum, if there is some gamma, if gamma is smaller than alpha, okay, then gamma is not an upper bound of L. Then gamma not an upper bound of L, and therefore gamma does not belong to B, right? Because otherwise it would be an upper bound. Therefore, alpha is smaller than or equal to x for every x in B. Okay, because if anything is smaller than alpha, it is not in B. Okay, so great. I have thus shown that it is smaller than every element of B. Therefore, alpha is in L because it is a lower bound. As it is a lower bound, Okay, and if alpha is smaller than beta, right, then beta is not in L, since A is the least upper bound of L. Since alpha least upper bound of L, right? Well, what does that mean? Therefore, any lower bound of L, any lower bound of B must be in L and must be smaller than or equal to and must be smaller than or equal to alpha, right? As it is the largest element of L. Therefore, alpha is the greatest lower bound of B, and therefore alpha is equal to infimum of B as required. Okay? So let me stop this one here. Next time we will start by defining some more things. We'll start off by defining fields, which will be a very interesting object in its own right. Okay?